Hello everyone, myself J. Vinay Kumar. In this presentation, we are going to learn about the Fleming's left-hand rule, the working principle of DC motor. First of all, let us know about DC motors. A DC motor is nothing but it's a machine which converts electrical energy into mechanical energy. Whereas in the previous presentations, we have learned about DC generators. Their DC generators converts mechanical energy into electrical energy. Here in a motor, it is mechanical energy will be the output. Okay, what is the principle here? Here the main principle is whenever a current carrying conductor is placed in magnetic field, then it experiences a mechanical force. It means conductor experiences a mechanical force, and this conductor tends to rotate, and this force will be in perpendicular to both the direction of current and magnetic field. And here the direction of force is given by Fleming's left hand rule, whereas in the generator it is given by Fleming's right hand rule. Here it is Fleming's left hand rule. Okay, let us see Fleming's left hand rule. In this diagram, it can be observed that there is a north pole and a south pole, and the lines between these poles are nothing but magnetic field. These lines are magnetic field lines, and here we can also observe a conductor which is placed in the magnetic field. And also the direction of current is shown. If we know the direction of magnetic flux and direction of current, then the motion of the conductor can be easily found. Here, the motion of the conductor is upwards. First of all, hold your left hand with all the three fingers, that is, forefinger, the middle finger, and thumb at right angles to one another. Here, then, the forefinger represents the direction of magnetic field, whereas the middle finger represents the direction of current, and the thumb indicates the direction of force. Mainly here we use the left hand rule to find out the direction of force if we know the direction of magnetic field and direction of current, which I have shown in the below figure. Now let us see the working of DC motor. In this figure, it is clearly represented that there are poles, that is north pole, with conductors, that is field conductors, placed in the pole shoe. Then from the figure 2, we can see that when current flows in the conductor, then a magnetic field is set up around the conductor. And in the figure 3, we can see the combined effect of both the fields, that is the field of main poles and also the field of armature conductors. In this figure, we can see here two poles. One is north pole and the other one is south pole, and this is the armature which is rotating in anti-clockwise direction, and these are the current carrying conductors on the armature represented by dots and also through some cross. This dot indicates that the current is flowing upwards, whereas the cross indicates the current is flowing in downward direction. Now let us see the working of a DC motor. When we start giving the supply to the terminals of a DC motor, then the field magnets are excited and this becomes, which develops an alternate, that is north pole and south poles as shown in the figure, and the armature currents will also flow in the armature conductors. Here in that figure we can see that the armature conductors which are under the influence of north pole are assumed to carry current in downward direction, and the conductors which are under the influence of south pole will carry current in upward direction, which are shown here as dotted conductors. Now the direction of the force can be given by applying Fleming's left hand rule. Here the small arrows placed above each conductor shows the direction of force, and each conductor experiences a force which tends to rotate the armature in anti-clockwise direction, which I am showing here in the diagram. This is anti-clockwise direction, and these forces collectively produce a driving torque which sets the armature rotating. From this presentation, we have learned about the principle of DC motor, that is, whenever a current carrying conductor is placed in a magnetic field, then it experiences a mechanical force, and this direction of force can be given by Fleming's left hand rule. We have already discussed about the Fleming's left hand rule. We also learned about the working principle of DC motor. Now let us see a small quiz on this presentation. In a DC motor, the mechanical output power actually comes from option A, field system, option B, air gap flux, and option D, back EMF, and option D is electrical input power. What is the answer? Yes, the answer is electrical input power. Now let us see the next question. That is, the middle finger of Fleming's left hand rule represents option A, direction of force, option B, direction of current, and option C, direction of magnetic field, and option D is none of the above. The middle finger represents the direction of current. Forefinger represents direction of force. Thumb represents, sorry, Forefinger represents the direction of magnetic field. Thumb represents the direction of force. Let us see the frequently asked questions from this presentation. One is state Fleming's left hand rule. Number two is explain the principle of DC motor. Okay. Now let us see the next topic. Already in the previous slides we have learned about the working principle of DC motor, Fleming's left hand rule, and in this presentation we are going to learn about the significance of back EMF and also the formula for back EMF and the other equations for the back EMF. Now let us see the significance of back EMF. Already we have discussed that when a supply is given to a DC motor, the field windings of the DC motors get excited and a current IA flows through the armature conductors and the torque is developed and which makes the armature conductors to rotate in the anti-clockwise direction. But when the motor armature rotates, these conductors also cuts the magnetic flux. We know that according to the Faraday's laws of electromagnetic induction, whenever a conductor cuts the magnetic field, an EMF will be induced in the armature conductors. And this EMF induced is nothing but it is the back EMF. That is, this EMF flows from the armature to outward direction. Now let us see this circuit. In this we can See, an armature which is given a DC supply with an voltage of V volts and the current is IA, that is armature current, and the resistance of this armature is RA. The EMF which is generated in the armature is given as EB. This is EB, which is generated in the armature and it is going outward. That's why I am showing this through an arrow, which is in upward direction. Whereas the other two, that is the voltage and armature current, will be in the downward direction. This voltage is exactly in opposite direction to the EMF induced. And this induced EMF is referred to as back EMF. I have shown this in an equivalent circuit. The armature circuit is equivalent to a source of back EMF EB in series with armature resistance RA put across a DC supply voltage of V volts. Here, if here there will be three conditions. If voltage V is less than EB, then this machine acts as a generator, and if the voltage V is greater than EB, then it acts as a motor. So as we now are studying regarding the DC motors, the applied voltage V must be large enough to balance both the voltage drop in armature resistance and the back EMF all times. From this equivalent circuit, the voltage V is equal to the back EMF plus the resistive drop in the armature. This equation I have written through applying KVL, Kirchhoff's voltage law. That is the sum of the algebraic sum of all the voltages and drops in a closed circuit is equal to 0. That's why here V is equal to EB plus IA RA, where IA is the armature current and RA is the armature resistance, and V is the voltage applied across the armature. We know that mainly this back EMF is mainly induced due to the generator action, and the expression for the back EMF can be given as EB is equal to phi Z NP by 60A, where phi is the flux per pole in Webers, and Z is the number of armature conductors, and N is the speed with which the armature rotates, and given in RPM, that is rotations per minute. And P is nothing but the number of poles, and A is the number of parallel paths. Already we have discussed about this equation in the first presentation. As we know, the back EMF is given as EB is equal to phi z n p by 60a, keeping all others as constant. The back EMF EB is directly proportional to the armature speed. That means if the speed of the armature is high, then the back EMF will be high, and the armature current, that is IA, is small. And if the speed of the armature is low, then the back EMF will be less. Therefore, the armature current is less. From this, it is clear that EB depends on the speed, and also IA depends on speed. So this back EMF EB acts like a governor, that is speed governor. It makes a motor regulating so that it draws as much current as required. From this presentation, we have learned about the back EMF, which is mainly induced due to the generator action, and also learned about the significance of back EMF. In a motor, the voltage applied should always be greater than the back EMF and the drop in the armature. And now let us see a small quiz on this presentation. If you answer this quiz, means the presentation is very clear for you. This question number 1 is, with the increase in speed of a DC motor. Option A, both back EMF as well as line current increases. Option B, both back EMF as well as line current falls, means it decreases. Option C, back EMF increases but line current falls. Option D, back EMF falls and line current increases. From the equation EB is equal to 5ZNP by 60A, it is clear that the back EMF is directly proportional to the speed, that is N. EB is directly proportional to N. So as the N gets increased, EB, the back EMF, increases. We know as the back EMF increases, the line current gets decreases. So the answer is C. Back EMF increases but line current decreases. Now let us see the next question, that is, if the back EMF in a DC motor vanishes suddenly, then the motor will. What happens if there is no back EMF? Start hunting, B, burn, C, run at high speed, run at very low speed. The answer is it gets burned. As the back EMF becomes zero, the current gets increased hugely, which makes the armature to burn. Now let us see the frequently asked questions. That is, what is the significance of back EMF in a DC motor? Means here we have to write about how this back EMF is generated and on what factors does this back EMF depends on, and the equations regarding the back EMF. It will be of about a 5 marks question. And also the second question, write a formula for back EMF in a DC motor. The formula will be 5Z NP by 60A is for EB, and also V is equal to EB plus IA RA. Okay, thank you very much.